This presentation will discuss intervention to prevent dam or levee breach. The presentation will present an overview of detection and intervention. We'll go through what detection looks like and discuss some typical intervention activities that can be taken during a flood event. For evaluation of this node of the event tree, unsuccessful detection or intervention leads to breach. A qualitative method of assessing the time for development of internal erosion will also be discussed, which influences the likelihood of successful detection, intervention, or repair. First, an overview of this node of the event tree. This node considers the likelihood that human efforts to detect and stop or slow the internal erosion process from breaching the embankment fail to work. Unsuccessful detection and intervention can be assessed as a single node or can be decomposed into multiple nodes. Intervention nodes may be functions of different stages. For example, observable evidence of seepage or leakage may be obscured by vegetation or tailwater inundation for low or high pools. Instrumentation and monitoring programs may be inadequate spatially or temporally to detect evidence even if it is observable. And if the evidence is observable and detected, intervention may be influenced by the physical ability to intervene or accessibility due to access roads being submerged by reservoir or spillway flow. It may be appropriate to consider both early and late detection of the internal erosion process. If late detection of the need for intervention occurs, heroic intervention will be required. If heroic intervention is estimated, you should provide a separate risk estimate because it would be irresponsible of a dam or a levee owner to manage a project or portfolio of projects based on the estimated risk assuming heroic intervention. Two examples of heroic intervention at dams are shown on this slide with dramatically different results. A very serious failure of a large portion of the embankment on the left side of the spillway occurred at Fontenelle Dam, as shown in the two figures on the right. Reclamation was able to lower the reservoir nearly 4 feet per day due to significant release capacity until erosion waned and stopped. The reservoir volume at the time of the incident was approximately 300,000 acre-feet. While the reservoir was drawn down, the eroded portion of the embankment was replaced and the foundation was grouted extensively. Only 45 feet of embankment remained between a sinkhole on the crest and the upstream face. The sinkhole was filled with upstream riprap. At Teton Dam, a wet spot appeared on the downstream face less than about 20 feet from the abutment. The wet spot quickly turned into active seepage and a hole appeared. As the hole grew larger, 2 bulldozers were dispatched to push boulders and material into the hole, but it continued to erode faster than they were able to fill it. The note in the bottom right corner of the photo reads, "After vainly trying to break an embankment of Teton Dam, 2 CAT operators back towards safety as their bulldozers slide into the widening gap." The dam failed shortly after this photograph. Despite many internal erosion incidents, USACE has a high rate of successful intervention. None of these incidents have resulted in a dam breach, however, several levee breaches have occurred. Success is primarily due to early detection of obvious signs of distress by visual inspections and rapid remedial actions. Rapid remedial actions have included drawdown of the reservoir, such as at Worcester Dam and East Branch Dam, placement of sandbag rings around seepage exits, and placement of filter materials over seepage exits. The role of intervention in USACE risk estimates is twofold. It helps to understand the potential benefits of intervention, but at the same time, the seriousness of the issue should not be masked by using intervention to reduce the estimated risk. This is the reason why risk estimates are prepared for both with and without intervention. Therefore, this node plays an important role in characterizing the risk. USACE manages its dam and levee portfolio based on the with intervention scenario. When evaluating intervention, it's important to consider during the risk assessment specific actions that could be taken to prevent a failure and their likelihood of success. By and large, intervention efforts have been successful in our inventory, and it's common to see an order of magnitude or greater reduction in risk when intervention is considered. Based on the USACE levee data reviewed so far, these failure rates were established for internal erosion PFMs with and without flood fighting as a function of levee height. For internal erosion through the embankment, the failure rate at a loading of 95% of the levee height is about 2% with flood fighting and 12% without flood fighting. For internal erosion through the foundation, the failure rates are about the same. And for both locations, the difference between failure rates with and without flood fighting is about 1 order of magnitude. The next set of slides will discuss detection. Internal erosion incidents have typically been discovered by visual observation, sometimes by the public. Here are some signs associated with each internal erosion process. For concentrated leak erosion, emergence of leakage containing eroded particles can occur on the downstream or landside face, around conduits, or at the downstream toe. For backward erosion piping, soil contact erosion, and suffusion, sand boils can occur at the downstream toe, or there may be other signs of eroded soil. Suffusion may also be evidenced by emergence of leakage or water on the downstream or landside slope rather than sand boils, unless the suffusion is in the foundation materials. For soil contact erosion and suffusion, crest settlement can occur. Sinkholes can occur with all internal erosion processes. And the sinkholes may be relatively benign, like from internal migration and suffusion, or they may indicate the erosion has already progressed and the time to failure may be small. Seepage or concentrated leaks may be obscured by rockfill, tailwater, marsh areas, dense vegetation, blankets, etc. Given that the evidence of internal erosion is observable, the following questions should be asked during a risk assessment. Is the project staffed or remotely operated? How often is the dam or levee observed or visited? How close does the public get? Are local officials such as police, park rangers, recreation staff, or the levee sponsor trained in dam or levee safety? Few cases have been detected by routine instrumentation monitoring, although it has happened. Over the long term, piezometer and seepage measurement trends can be indicative of slowly developing internal erosion failure modes. In addition to the location of the instrument, the frequency of instrumentation readings is an important consideration. Data resolution may be increased with more frequent readings if an instrument experiences highly variable conditions as shown in this series of plots. Monthly plots yield long-term trends, but correlations may be difficult to discern. For example, tailwater at a dam may change frequently and rapidly due to power generation or spillway operations. If a piezometer reading is taken only during low tailwater and the tailwater reading is taken only during high tailwater, the relationship between the two variables is obscured. Daily readings provide higher data resolution for a rapidly changing instrument. However, a daily interval is typically the highest practical frequency for instruments that are read manually. Daily readings should typically be performed during a modification project if instrumentations are read manually, for limited periods of time during high water events, or for noted unusual instrument readings requiring further investigation. Automatic data acquisition systems, or ADAS, make possible a much higher instrumentation reading frequency than is practical for manual reading. Next, we'll take a few slides to discuss intervention activities and how we take those into account during risk assessment. Intervention efforts are likely to occur during all phases of the internal erosion process. Given the seepage is observable and detectable, the likelihood of successful intervention depends on several factors, including the time available to intervene based on the rate of erosion, which is a function of material erodibility, the accessibility of the project in the internal erosion entrance or exit, and the availability of personnel, equipment, and materials. Reservoir drawdown below a flaw or to reduce hydraulic gradient is the most successful intervention for large dams. The size of the flood event is also important. Large events can have regional impacts which can limit the availability of personnel since they may be spread out over several projects. Accessibility is a key consideration for the ability to intervene. On the left, we see that Bolivar Dam's downstream toe is inundated by Dover Dam's pool. There's a very narrow time window to mobilize and place a filter during a seepage incident. In the top right, we see a low water crossing that's present at the outlet channel of Green River Dam. In the event of an emergency, large releases may prevent access to over 2/3 of the downstream toe. An access road was subsequently constructed over the conduit to address this scenario. In the bottom, we see that access from the left abutment of Mohawk Dam will be cut off by spillway flow, and access from the right abutment will be cut off by the roadways at lower elevations being submerged by the reservoir. Emergency stockpiles of materials for flood fighting can become inaccessible and inundated as well. Some typical remedial actions that we can take are shown on this slide. In addition to drawing the reservoir down, some structural actions include building reverse filters over boils or areas where eroding material is emerging from the foundation or the embankment, building a weighted berm to reduce the likelihood of heave, slope instability, or unraveling, and dumping granular material such as sand, gravel, or rockfill into the upstream side of sinkholes to try to block them. More than one of these measures may be used together. Now we'll discuss time of development of internal erosion. The likelihood of detection and successful intervention or repair depends on the time from when the internal erosion process may be detected to when breach begins. Fell et al. In 2001 and 2003 studied case histories of failures and accidents for piping in the embankment, foundation, and embankment into the foundation. Based on case histories and an understanding of the physical processes, they developed guidance on the time for progression beyond when a concentrated leak is first observed, erosion has initiated and filters have not stopped it from continuing, and the development of a breach. The rate of erosion is an important consideration, and the excess shear stress equation can be used to estimate the rate of pipe enlargement in the progression phase. This slide is also presented in the progression presentation. Based on whole erosion test results, this figure shows the approximate time for a pipe to enlarge from 25 millimeters to 1 meter in diameter as a function of erosion resistance and hydraulic gradient based on the assumptions shown. Erosion resistance increases from left to right. The approximate time to erode to 2 meters is about 20% greater. Even in the most resistant of soils, enlargement occurs in only 100 to 500 hours, or 4 days to 3 weeks. This table presents usual times for initiation and continuation of internal erosion by location of the internal erosion. Fell et al. 2003 developed an approximate method to estimate the time for progression of internal erosion and development of a breach in embankment dams. It's summarized here and on the following slides for each of 4 factors influencing time for development for progression and breach. 1. Ability to support a roof. 2. Rate of erosion. 3. Upstream flow limiter. And 4. Breach time. Step 1 is to assess the ability of the surrounding soils to support a roof. In this, we utilize the previous evaluation from the progression phase. For step 2, we have some qualitative times for erosion for gradients of 0.2 and 0.5 along the pipe as a function of soil classification. In this table, erosion resistance increases from top to bottom. Therefore, the rate of erosion also decreases from top to bottom. These qualitative terms are used in the approximate method. In step 3, we assess the likelihood of any upstream flow limitation. We utilize the previous evaluation from the progression phase. Finally, step 4 assesses the breach time. These tables provide qualitative likely breach times based on material descriptions and then converts the qualitative likely breach times into equivalent times in hours, days, weeks, months, or even years. These qualitative terms are used in the approximate method. This slide shows the limitations of the approximate method. Most of the case studies were for breach by gross enlargement, and therefore the method is really only applicable to cases where the breach mechanism is gross enlargement. The method is considered reasonable for final breaches by slope stability following development of a pipe, but it will likely underestimate the time for breach by sloughing, since breach by sloughing is a slowly developing mechanism that could take days to weeks to lead to a breach. The following table from the Best Practices Manual can be used to help assess the likelihood of unsuccessful detection and intervention. It can be used as a starting point, but the risk team must develop project-specific more likely and less likely factors to guide subjective probability estimation. The factors in this portion of the table address detection. And the factors in this portion of the table address physical intervention actions. To wrap up, I want to have a short discussion on intervention as it relates to levees. Intervention is part of the design for many levees, so there's some questions that we should ask when evaluating this node for a levee system. Are flood response efforts assumed in the design of the levee system? Are the procedures for identifying and mitigating uncontrolled underseepage documented in the O&M manual? Does the levee sponsor and the Corps have experience in successfully implementing intervention activities? What is the working relationship between the levee sponsor and the Corps? And does USACE provide technical and resource assistance during flood events? These are all considerations that should be taken into account during risk assessment of a levee. This concludes the intervention presentation.